There are some very obvious hazards when fighting a fire. But what else do we have to consider when planning and organising firefighting teams? The way we tackle fires depends on where the fire is. How are things done differently in each location? Ideally, you should watch this title with at least 2 of your colleagues, so that you can discuss what you've seen. We will ask you some questions at the end of the film, so that you can reflect on what you have seen and heard. In addition to the most obvious hazards from firefighting, such as the smoke, flames and heat, we need to be aware of additional hazards during the firefighting process, and take steps to reduce or eliminate the risks from them. Heat exhaustion is one of the least obvious personal hazards. Firefighters need to wear a heavy insulated fireman's outfit to protect them from the heat of the fire. However, they will get very hot inside the suit, and this can lead to dehydration. The humid atmosphere also means crew members do not lose heat through sweating. To protect crew from heat exhaustion, it's essential to monitor the time a person spends in a fireman's outfit and firefighting with a full SCBA set on. Realistic drills prepare the firefighter for wearing all the equipment and feeling the effects of it. When firefighting, it is also essential that you drink water to stay hydrated. Carbon dioxide released into the space to fight a fire lowers the oxygen content and will not support life. All crew, particularly those in the engine room, must know that when a CO2 alarm goes off, the space should be evacuated immediately. The CO2 must not be released until all crew are accounted for, and only on the master's orders. Firefighters must consider the steam that is produced when water hits hot surfaces, as this will burn exposed skin. For this reason, there should always be a proper fireman's outfit available with full body protection. Realistic training also prepares a person for a steam cloud that is produced when water is sprayed onto a hot surface. Guidance should also be given on using water spray rather than a jet of water, as this reduces the intensity of the steam produced. Water sprayed onto a fire will cause gases and smoke to spread away from the fire. So ventilation flaps should be closed and the air supply units should be stopped. If possible, the vessel should be turned so that the smoke and gas blow away from areas where the crew are located. Another hazard is that the air supply may run out or the SCBA may fail. Wearing an SCBA set for a realistic time allows the wearer to gauge their air consumption for the duration of firefighting. A drill should emphasize to the wearer that when a warning whistle sounds, the wearer should already be out of the space. It is not a sign to return to safety, as there may not be sufficient air left to do this. The wearers of self-contained breathing apparatus should practice various operations to assess their rate of consumption. This will vary with the amount of work the wearer is doing, the level of training, personal fitness, and the amount of stress the wearer is under. On average, a person uses 40 litres of air per minute. If a BA set has a cylinder pressure of 300 bar and the whistle sounds at 55 bar, there is 245 bar of working pressure. Experience with fires on board shows that the level of air used to get to the fire seat is the same as that needed to return. The rest is used for firefighting. Air use must be monitored at all times. If a fire is out of control or entry should not have taken place, there is a danger of being overcome by fire. There are two protection methods to stop this from happening. If a risk assessment shows that a fire is extensive, entry should not be attempted. Secondly, firefighters should always work in pairs as a minimum. This ensures that there is always a buddy to assist or raise the alarm. There should also be a lifeline that acts as a guide back to the outside if the firefighter becomes disorientated. There are a number of other hazards that can occur due to the actions taken when fighting fires. Stopping ventilation to a coal cargo can cause methane gas to build up. When using opposing streams of water, a jet can push smoke and flames away from one firefighting team towards another. Chemical fire suppression agents mixing with other chemicals can produce a dangerous gas. If dangerous goods are carried and the incorrect extinguishing medium is used, there is a real danger of making a fire worse. When chemicals are carried, it is important the correct information is available with regards to the type of extinguisher medium to be used. A fire hose discharges a lot of water. The flow rate is dependent on the hose diameter, the pressure in the line, and the type of nozzle in use. SOLAS requires that there should be a maximum discharge rate on certain types of vessels of 140 cubic meters per hour. At this flow rate, 2 fire hoses can deliver 150 tons of water every 30 minutes. 4 fire hoses can deliver 300 tons of water every 30 minutes. On some vessels, the flow rate is significantly higher, but this can make a hose more difficult to handle. Depending on where the water is being directed, some may go overboard, some become steam, but some will stay on board. The additional weight of water used to fight a fire can adversely affect a vessel's stability. At the very worst, top weight and free surface effect can result in a capsizing lever. This is why stability should be regularly assessed during firefighting operations. Any accumulated water should be allowed to drain away, or be pumped straight overboard. In an emergency, the safety of the ship and crew come first, and there is provision in MARPOL that allows us not to have to discharge all of the water through the oily water separator. Obviously, we still need to take all reasonable steps to avoid pollution. During a fire, there are a number of stored goods that need to be considered. These include such things as paints and thinners found in the paint locker or storeroom, drums of grease and oil lubricants, and cylinders containing compressed gas such as LPG, oxygen, and acetylene. There will also be dry combustible stores, cleaning room stores such as boxes of aerosols which might use flammable propellants, and other combustible stores. Some dry cargoes present particular hazards. On a vessel carrying coal with a fire in the accommodation, steps have to be taken to stop the fire spreading to the coal. Boundary cooling is an effective way to do this. Any dangerous cargo on board should always be treated in accordance with the IMDG code. Some items, such as phosphorus, will burn if the product is exposed to air. Lithium will burn vigorously if exposed to water and air, and magnesium will burn underwater. Any flammable hydrocarbons on board should normally be stored well away from the accommodation. There should be a plan to remove them from a fire location or prevent the fire from getting anywhere near them. Cylinders containing compressed flammable gases are very dangerous, as they can explode if they get heated. This is known as a boiling liquid expanding vapor explosion, or a BLEVE. It causes the pressurized container to disintegrate, causing the sudden release of gases to erupt into a ball. Boundary cooling and direct cooling can be used to cool pressurized containers, if we can start this before heat builds up, so that the fire party is not at risk. Here is a reminder of the main learning points from this chapter. The risks to the firefighting teams should be properly assessed and minimized or reduced before committing teams to fight a fire directly or enter a space affected by fire. The stability of the vessel must be checked and maintained when using water to fight a fire. Additional risks can come both from hazardous goods and some of the ship's own stores, such as cylinders containing compressed gas. Exactly how we fight a fire depends a lot on where it is, so let's take a look at some common locations where we might have to fight a fire. Planning for firefighting and realistic drills should cover all of the areas we have on board ship. With a cargo fire, the accommodation has to be protected from smoke and toxic fumes. Another factor with location is restricted access. It is important for a firefighter to gain easy access when directly fighting a fire, and always to have a clear, easy escape path. Electrical systems and fuel supplies must also be considered. Firefighting may take place near to electrical power. Unfortunately, every year, professional firefighters are electrocuted. The danger comes from the use of water dispensed via a hose or portable fire extinguisher if the system is still live. Electrical systems can also involve high voltage, which is very dangerous. An electrical motor or switchboard fire could occur with power still present. In an area where firefighting is to take place, electrical systems should be isolated before water is used. On a vessel, there is lots of fuel stored for propulsion. When we consider the fire tetrahedron, we see that this is one of the 4 elements required for the combustion process. When a fire breaks out involving leaking fuel, systems should be shut down to stop the supply of oil to a fire by using local or remote stops. Although fighting an accommodation fire is aided by the number of fire doors and any fixed extinguishing system, there are a number of factors that must be considered. These include the number of spaces to which the fire can spread and the number of obstacles preventing people from moving around. People can become trapped in their cabins due to smoke in an alleyway, and flashovers are common when a door is opened with a fire behind it. Remember, the bridge is the control point of the vessel, and this is where firefighting activity is normally coordinated from. As it is at the top of the accommodation, smoke and heat from the fire will rise towards the bridge. Accommodation fires often start small and are noticed before they take hold. If allowed, a successful initial attack using a portable fire extinguisher may be effective. If they are too large to fight with a handheld extinguisher and a fixed system is fitted, then activate the fixed system and also deploy backup fire parties with hoses for boundary cooling. Before tackling a fire in a cabin using fire hoses, make sure that all sources of electricity have been switched off. The hose party should then stay low down in the alleyway. Crack open the door and direct a spray nozzle towards the deck head to cool hot gases. Close the door to allow the steam produced to smother the fire. Further applications of spray reduce the hot gases until it is safe to open the door and attack the fire directly. Class A fires are common in a cabin, and so you must ensure that all heat is removed, otherwise it can easily reignite. An engine room has many inaccessible spaces and steel surfaces to gather and conduct heat. Smoke, gases and heat are often free to rise inside the generally large volume found in an engine room. Engine room fires are usually associated with burning oil, often caused by a broken pipe union or spilled oil. This type of fire can escalate very quickly. With heat and large amounts of thick black smoke, an engine scavenge space or boiler economizer fire can be very ferocious, with burning metal at very high temperature. With an engine room fire, loss of firefighting and electrical supply capability is a real threat if emergency systems are not started. If an engine room fire is noticed soon after starting, a small fire can be attacked with a portable fire extinguisher. If not, the space should be evacuated and all personnel should be accounted for. Fuel supplies should be shut off, ventilation stopped, flaps and doors closed, and machinery stopped. The fixed extinguishing system should then be used. If a gas is used for this, there is very little cooling effect, so we need to allow time for the engine room to cool down. Otherwise, reignition may take place when we try and re-enter. A fixed water spray system both smothers a fire and reduces the temperature. Boundary cooling should be applied to the areas around the engine room, and temperatures monitored until it is obvious that the fire is out. If entering the engine room to tackle small fires, then enter from below, for instance from the shaft tunnel. Since hot air rises, this is likely to be the coolest part of the engine room, and there is also less risk of smoke and heat entering the accommodation. Teams should be wearing breathing apparatus and protect themselves with water spray from fire hoses. One special case of a fire in the engine room is a boiler economizer fire, where very high temperatures cause leaking water to separate into hydrogen and oxygen. This further fuels the fire, causing steel to burn. Water cannot be used to extinguish this type of fire. It is best left sealed up with water flow stopped and left to burn itself out. Boundary cool the areas outside the engine room around the exhaust uptakes to stop the fire spreading. On deck, fires can arise on oil and gas carriers, when spilled or leaking products ignite. On oil tankers, collisions often result in tanks being ruptured. Sparks can then cause the oil cargo to ignite. The potentially large volume of oil makes this sort of fire very difficult or impossible to extinguish. On a gas carrier, flange seal leaks that catch fire can be extinguished by turning off the flow of gas. Regardless of location, with any fire, the product transfer should be immediately stopped. In port, there are usually strict requirements that a terminal has in place, both to prevent and fight a fire. Again, small fires on deck can be tackled using portable extinguishers. But larger fires are best attacked using the fixed system. Deck fire monitors are capable of ejecting relatively heavy foam over a large distance, blanketing the deck. Accommodation blocks are often protected with a water spray curtain to stop them heating up. A cargo hold can be filled with one product, such as coal. Or it could contain several products, such as those seen on a breakbulk vessel. Any fire in a cargo hold can be deep-seated and present a number of difficulties. When a fire starts in closely packed objects, it is difficult to fight, as extinguishing media cannot get close to it. As with a cabin fire, opening a hatch lid or access door can cause a flashover. Lastly, it is difficult and dangerous to send firefighters into the hold space with a hose. The best course of action is to shut off ventilation, close flaps, and flood the space using the fixed extinguishing system. Boundary cooling is essential to stop heat passing through bulkheads into adjacent holds. Further considerations include keeping a reserve of extinguishing gas, as a hold fire can take several days or weeks to extinguish, and identifying explosive cargo and taking as many steps as possible to stop a fire from getting close to it. If there is any doubt about an explosion risk, all firefighters should be withdrawn from the scene. As the floor of a container is possibly made of wood, it can burn through in the event of a fire. The actions to take with a container fire will depend on its location, either on deck or in a hold. Boundary cooling should be immediately started to stop other containers from overheating and their contents catching fire. A hole can be made in the side of a container, where a suitable extinguishing medium can be added. Here is a reminder of the main learning points from this chapter. Our firefighting tactics depend on where the fire is, so realistic fire drills should be held for all types of location we have on the ship. Isolating electrical supplies in and around the area of a fire is essential to eliminate the risk of electric shock to the firefighting teams. Gas-based fixed firefighting systems for the engine room are effective at putting fires out, but have little cooling effect, so the space needs to be left closed up and boundary cooling applied. Any space where there has been a fire, especially if a gas firefighting system has been applied, will be deficient in oxygen, so a BA set should always be worn and enclosed space entry precautions taken. How could the fire drills on your ship be improved? Do they cover all locations and involve all the crew, in both their main duties according to the muster list and any backup roles? Based on the drills on your ship, how long do you expect the air supply on your breathing apparatus set to last? Do you know where all the flammable gas cylinders and significant quantities of aerosol cans and highly flammable materials are kept on your ship? Are there any of the hazards we have covered here which are not covered by the training and drills on your ship? Is there anything different in what you practice on drills compared to the generic examples we've seen here?